Welcome back to the Deep Dive. Today we're jumping into, well, the incredibly fast world of AI. It seems like everyone's racing to build models that are, super smart, but also don't need a supercomputer to run.
That's the dream, isn't it? Power and efficiency.
Exactly. And that brings us to RWKV. It's this really fascinating architecture making, what they call it, a hybrid. It apparently mixes the best of, like old school RNNs and modern transformers.
That's a good way to put it. It's a very clever blend.
So for you listening, our mission today is to really unpack the latest in RWKV, specifically version 7, Goose, and 8, Heron. We want to get into how they're tackling some, frankly, frustrating limitations in current LLMs.
Right, and hopefully show some of those aha moments in how they gain efficiency and capability.
Yeah, because these aren't just small updates, are they?
Not at all. These feel like pretty significant leaps conceptually. They give us a real glimpse into how future AI might be built, maybe deployed much more widely.
Okay, let's start with that core idea then, this hybrid thing. You said it acts like an RNN for inference, but trains like a transformer. Can you maybe break that down a bit more? How does that actually work?
Sure. So the core insight is this dual nature. When RWKV is actually running, doing inference, generating text, it processes information sequentially, one token after another, like a classic RNN.
Okay.
And that means constant memory use per token, constant processing time per token, and theoretically, an infinite context length. Crucially, it avoids the need for that big key value cache that transformers use.
Ah, the KB cache. That's the thing that eats up all the memory with long trumps, right?
Precisely. It can become enormous.
Yeah.
But RWKV doesn't need it for inference. However, when you're training the model, it transforms effectively and behaves like a transformer.
Meaning it can be trained in parallel.
Exactly. You can blast it across GPUs for super efficient training, just like a standard transformer.
So it's like, okay, a transformer needs this huge memory backpack that gets heavier and heavier, but RWKV just has a tiny notebook for inference, and it trains super fast.
That's a pretty good analogy, yeah. It gets around that fundamental trade-off. Efficient training or efficient inference. RWKV aims for both.
Which is huge for long texts or running AI on, say, your phone.
Definitely. Edge devices, long document analysis. It opens up a lot of possibilities.
Okay, fascinating. So let's move on to RWKV 7, Goose. It introduces something called meta-in-context learning. Sounds fancy. What's the idea there?
Right. So think about how models sometimes struggle with really long-range dependencies or adapting quickly to new patterns within a prompt. There's this theoretical limit, sometimes called the TC22 limitation, that affects attention mechanisms and even newer architectures like Mamba.
Okay, a bottleneck.
Kind of.
Yeah.
RWKV7 tries to sidestep this. With meta-in-context learning, it's almost like the model is test-time training, a little internal model, while it's processing your prompt. It learns how to adapt on the fly.
Learning to learn in context.
You got it. It's inspired by some classic ideas, fast weights, Hebbian learning, but implemented in a way that still trains efficiently on modern hardware.
And does it work? What are the results like?
Pretty impressive for its size. They had a 2.9 billion parameter version, which is relatively small these days, achieves state-of-the-art on multilingual tasks.
Wow, so multilingual.
Yeah, and it matched SOTA for its size class on English tasks, too. It shows you don't necessarily need a behemoth model for top performance if the architecture is smart.
And I saw a striking number for document understanding. RWKV7, an even smaller one, 0.16b parameters, crushed a benchmark called record.
That's right, 72.1% accuracy compared to around 61.8% for a similar-sized Mamba model on that document question-answering task. It really highlights its strength with longer contexts.
So it's better at tracking information over long stretches.
It seems so. The architecture allows for state tracking and recognizing patterns like regular languages that standard transformers can struggle with. It's got more expressive power in that sense.
Okay, Goose sets a high bar. Then comes RWKV8, Heron. What's new there? I'm hearing about deep embed and deep embed attention.
Yeah, Heron builds on Goose, pushing efficiency further. Deep embed is one key piece. It's a way to scale the outputs of the feed-forward network layers using a specific vector for each token.
How does that help?
They call it essentially free performance. It adds a lot of parameters, which sounds bad, but these parameters can be mostly offloaded to regular RAM or even an SSD during inference.
Ah, so they don't hog the expensive GPU VRAM.
Exactly. Zero extra VRAM needed, they claim. which makes it much better for edge devices than, say, mixture of experts, which needs a lot of VRAM.
Mm.
The performance graphs show it consistently improves the loss, suggesting it really is getting gains without the typical hardware costs.
Like getting stronger without needing more VRAM makes sense for smaller devices.
Mhm.
And deep embedded attention, DEA.
Right, DEA is a twist on attention designed for these hybrid models. It uses an incredibly tiny KV cache.
How tiny?
We're talking maybe 64 values total for a reasonably sized attention head. That's like a ninth of the cache size a standard attention mechanism might need.
Only a ninth. But does it still help with long context?
Apparently, yes. The data shows that even this tiny cache significantly helps the model use long context better. The loss keeps decreasing further out into the sequence, which is what you want to see.
So, better long context understanding with a minimal memory footprint.
That's the idea. And the ultimate goal for RWKV8, the really ambitious part, is to achieve that improving performance on long context with 0 KV cache at all.
Wow. Okay, so wrapping this up, RWKV7 and RWKV8 seem to be genuinely pushing boundaries. They're blending architectures to get high performance and high efficiency, especially for long sequences, and importantly, on devices that aren't giant servers.
Exactly. It points towards a future where powerful AI isn't just in the cloud. Think smarter assistants on your phone, maybe wearables that can understand complex instructions or summarize long reports locally.
It really makes you wonder, doesn't it? As we head towards AI being everywhere, what kinds of truly transformative things become possible when we have models with effectively infinite context that can run on almost anything? How does that change how we find, process, and even think about information?
That's the big question. It could reshape our relationship with knowledge itself.
Definitely something to ponder. Thanks for breaking that down.